Hi everyone. So we're going to start with the idea of a limit, right? So this is the first new concept we're going to talk about in calculus. And before we even get to the idea of what a limit is, we're going to start talking more about motion, in particular the concept of average velocity. Right? And the average velocity is just your change in position over your change in time. Right. So as an easy example, well, for starters, suppose you're in a car, right? And you travel, let's say 200 miles on a trip that takes, let's say 5 hours, right? So we have our change in position. In this case, you can call that the distance. That's how far we traveled. And the 5 hours is the time. So, so just divide the distance by time. In fact, we'll just call that the average speed. Right? So distance divided by time. Right? So 200 miles divided by 5 hours gives us 40 miles per hour. Right? So this is our average speed over that 5-hour trip. Right? So on average, we were traveling 40 miles per hour. Right? So it's unlikely that we were traveling 40 miles per hour for the entire 5 hours, right? That's why it's an average speed. So, so sometimes we were traveling faster than that, and other times we were traveling slower than that. But on average, we were traveling 40 miles per hour for the entire trip, for the entire duration. Right. So notice that I changed the word velocity to speed here, and maybe I should clarify that. So a lot of people just use them synonymously, right? Speed and velocity. Velocity might just be a fancier word for speed. But mathematically, they mean something a little bit different, right? So notice that speed is the distance divided by the time, and velocity is the change in position, right? So here's a good idea for the difference, right? So we travel 200 miles in 5 hours, and let's say we then return. We return home. So now we traveled 400 miles, and let's suppose it took a little bit shorter to get home. Let's suppose it took 4 hours, right? So 5 hours to get there, and 4 hours to get back. So that means a total of 9 hours, right? So my calculator says 400 divided by 9 is about 44.4, I'll approximate here, 44.4 miles per hour. Right. So notice that's a little bit faster because it took less time on the return trip. Right. Okay, so this is still our average speed. Right? It's the distance we traveled divided by the time. So we traveled a total of 400 miles. That's the distance. And the time for the round trip back and forth was 9 hours. Okay. So what's our average velocity? Right? Our average velocity is the change in our position. So what is our change in position? We started at home, right? So we can call that position 0, right? And we ended at home, right? So we didn't get anywhere, right? We're in the same place we started, right? So our change in position, right, is 0. In the end, right, you can call this the net change in position or displacement, right? It's the difference in the place we started and the place we ended, right? So 0 miles. And of course it took 9 hours, right? So that's the time. So 0 divided by 9 is 0. So 0, sorry, I'm running out of space here. So this is equal to 0 miles per hour. So that's our average velocity, right? So that's the difference, right? Speed is always going to be some positive number because distance will always be considered positive, right? It's how far we traveled, right? We traveled 400 miles, right? But we traveled 200 miles, right? So we start here, we traveled 200 miles to our destination, right? And then we traveled 200 miles back. So a total distance of 400 miles, right? But our displacement was 0 because we ended at the same place we started. Okay. So yeah, slight difference between distance and displacement, and that's the difference between speed and velocity, right? So distance will always be positive, and velocity could be positive or negative. It just depends on what direction you're traveling in, right? So if I'm starting here, and I call that 0, and let's say I travel backwards, if that's possible, for even, let's say, 2 miles, right? Then I end up at negative 2 miles, if to the left is considered backward. If I travel to the right 2 miles, then that's considered positive. Okay, so velocity could be positive or negative, or 0 in this case, right? But distance will always be positive, so speed will always be positive. Okay, I just wanted to make that clear in case you're a little fuzzy on the difference between velocity and speed. Okay, so now I want to do an example of calculating the average velocity, right, for a given position function. So, right, so this is the formula for average velocity, and let's suppose that we know our position at any given time. So for position, I'm going to use the symbol s, right? And it's a function of time, right? So in this case, as our first example, right, suppose the position function is given by 2t cubed minus 5t squared. Okay, so this just tells me where I am at any given time. And let's actually provide units here. In some cases, right, I'll leave off the units. But in most cases, we want to know, whether we're dealing with inches or miles or feet or meters or kilometers, right? So let's say this is in meters, right? And t will be in time. So s is in meters, and t is in, let's say, seconds. Okay. Right. So for starters, we want to know where we start, right? So where we start depends on what time we consider to be the first time, right? Our initial time. I mean, it could be whatever we want, right? We can say we're starting at t equals 23 seconds. But it probably makes more sense to say the initial time is just 0 seconds. Okay. So where are we at 0 seconds? Well, just plug in t equals 0, right? We get 2 times 0 cubed minus 5 times 0 squared, and that's just 0 meters. Okay, so we're starting at position 0, which just makes sense, right? We can calculate where we are after 1 second. So just plug in 1. So this is going to be 2 times 1 cubed minus 5 times 1 squared. So that's going to be -3 meters. Now, what does that mean? It means we've gone 3 meters backwards, right? Whichever way backwards is considered, right? So if this is, we're starting at 0, in 1 second we've traveled backwards 1, 2, 3 meters. Okay, so where are we after 2 seconds? Right, again, just plugging in t equals 2 into the function. Right, we get 2 times 2 cubed minus 5 times 2 squared. Okay, so that's 16 minus, 5 times 4 is 20, so 16 minus 20 is -4 meters. Okay, so we've gone a little bit further backwards. All right, and I'll do one more, right? So after 3 seconds, this is 2 times 3 cubed minus 5 times 3 squared. So 2 times 27 minus 5 times 9. So this is, I think, 54 minus 45, which is 9 meters, positive 9 meters. So, yep, so from the second second to the third second, we went all the way back to positive now, positive 9 meters. Okay, so this is good enough. In fact, I'll just very quickly do one more. After 4 seconds, you'll see we're even further away. And this is 48 meters. All right, so this just tells us where we are at any given time, right? So now we can calculate our average velocity. So when we're asking for the average velocity, we have to give a time interval. We have to say what time we're starting and what time we're ending. So let's say we're starting at, again, t equals 0 seconds. So we want the average velocity from t equals 0 seconds to, let's say, t equals 3 seconds. Okay, so the time interval is from 0 to 3, using interval notation, right? All right, so using the formula, right? What we're going to do is we take the displacement divided by the time. So the displacement is the difference in position, right? We're going to plug in 3 into the position function. And then we'll plug in 0 and just subtract, right? And then take the difference in the time, right? That's just 3 minus 0 seconds. Okay, so I already calculated S of 3, right? That was the 9 meters here. And S of 0 was 0 meters, right? And this is, well, 3 seconds minus 0 seconds. So we get 9 divided by 3. This is 3 meters per second. So that's the average velocity in the first 3 seconds. Okay, so in general, we calculate the average velocity given the position function, right? And let's say this is from time t equals a to t equals b, right? This is just s of b minus s of a divided by b minus a. Right, so b minus a is just the difference in the time, right, where time varies between a seconds and b seconds. Right. And then s of b is your final position. and S of A is your initial position. If I can spell initial position. Right, and so the difference between the final position and initial position is what we call displacement, and it may or may not be the same as the distance. Right. In fact, in this example, it isn't because we've traveled backwards and forwards, so the distance is not the same as the displacement. Okay, yeah, so keep this formula in mind because we're going to use it over and over again. I mean, in fact, we already used it here for the particular case when right, A is 0 and B is 3. Right? Okay, so let's use maybe two different times. Let's suppose A is 2 seconds and B is still 3 seconds. Right. Okay, so, you know, it's a different time interval, and so we expect to get a different average velocity. Average. Right, so this is just going to be S of 3 minus S of 2 divided by 3 minus 2. I'm just plugging into this formula here, right? Okay, so S of 3, once again, is 9 meters. And S of 2, I forgot what that was. That was way up. Oh, sorry. That's 1. Yeah, S of 2 was negative 4 meters. Okay. So, yep, be careful. This is 9 minus negative 4 meters divided by 3 seconds minus 2 seconds. So 9 minus negative 4, 9 plus 4 is 13 meters divided by 3 minus 2, that's just 1 second. So the average velocity on this interval from 2 to 3 seconds is 13 meters per second. Right. You'll notice that's actually faster than from 0 to 3 seconds. Okay. All right. So we can do a lot of examples of these. In fact, you're going to be doing a lot of these for homework, right? And all of these examples, these two examples here, are calculating average velocity, right? So this is a velocity during some trip, some time interval, right? It could be a long interval, right? Instead of 3 seconds, it could be 3 hours, or right, some very long time, or it could be a very short time. It could be, in this case, 1 second, right? 3 minus 2, a 1 second. Sorry about the sloppiness there, right? But we can even go shorter than that. We can do a half a second or a tenth of a second, right? And it might not seem obvious why we would want to do that, but you'll see it'll make sense later, right? So, and in fact, what we want to calculate eventually is not the average velocity over an entire journey, entire trip. We want to know how fast we're going at any given moment in time. Okay, so right in the first example where we talked about the car traveling 200 miles in 5 hours, right? That's the average speed or the average velocity, right? 40 miles per hour for the entire trip. But if I'm in my car and I look down momentarily at the speedometer and it says 52 miles per hour, right? That's fine. That's how fast I'm traveling at that moment that I looked at the speedometer, right? So that doesn't contradict the average speed, right? The average speed is for the entire trip, right? Just the total distance divided by the total time. But at any given moment, I could be traveling faster than that or slower than that. Okay, so at the moment I look down and measure how fast I'm traveling, right, we call that the instantaneous velocity. So that's our goal. right, to calculate the instantaneous velocity. So this is the velocity at a given moment. Right, at a given instant or moment. In time, right? Right, so this could be at some time. I'll call it, I'll just call it capital T, I think. Right. All right, so this is what we eventually want to be able to calculate. Right, so let's look at our position function again. It was 2t cubed minus 5t squared, so I'll just copy that down. Right, and we want to find, let's say, the instantaneous velocity at, in this case, I'll use capital T, is, let's say, 3 seconds. So we want to know how fast we were moving, how fast we were going at 3 seconds. Okay, so what can we do? Well, the only formula for velocity we have is this one here, but this is for average velocity, and you'll see why that this doesn't work, right? So let me copy down the formula for average velocity here. Right. So for the average velocity, we need 2 moments of time, right? We need our starting time, t equals a, and we need our ending time, t equals b, right? From a to b. But we don't have that here. We only have one time. T equals 3 seconds. So in this case, we can say, well, both a and b are the same time. They're both 3 seconds, because that's the only time we have here. So our average velocity would be s of 3 minus s of 3 divided by 3 minus 3. So s of 3, if I remember right, was 9 meters. Yep, just checking. So this is 9 minus 9 over 3 minus 3. And we get 0 divided by 0. Right, we're dividing by 0. We know that's bad, right? So we don't get any, right? We don't get a number here. So trying to calculate the instantaneous velocity using the formula for the average velocity was doomed to fail here, right? There's no way we can do that. Right? We ended up with this meaningless number, 0 divided by 0, right? Okay. So, right. So what can we do? Well, right. So here's a kind of a clever idea. We're going to calculate the average velocity, but we're going to do it over sort of a tiny time interval, right? As I said earlier, this interval from A to B can be a very long interval, or it can be a very short interval, right? It could be 3 seconds or 3 hours, or it could be even shorter than 1 second. It could be half a second or a tenth of a second, right? And that's the idea here, right? So for starters, let's use the interval, right? So we already did 2 to 3, but let's do 2.5 to 3, right? So A is 2.5 and B is 3. Okay, so what's the average velocity? And in fact, let me make sure we know that this is average velocity from 2.5 seconds to 3 seconds. Okay, so using the same formula, s of 3 minus s of 2.5 over 3 minus 2.5. So we know s of 3 was 9. We never calculated s of 2.5, but we can do that now. And oddly enough, it's just 0. Right? So plug in 2.5, you get 2 times 2.5 cubed minus 5 times 2.5 squared. And that turns out to be exactly 0, according to my calculator. Right. So if you were wondering, right, because at time t equals 0, we're at 0. At t equals 1, we're at -3, so we're going backwards. And at 2 seconds, we're at -4. And at 3 seconds, we jump all the way back to 9, right? So this is at 2 seconds, this is at 3 seconds. So somewhere between 2 and 3 seconds, we have to pass back through 0 again. And as it turns out, it was exactly halfway between, 2.5 seconds. So that's what happened there. All right, so we end up with 9 meters in 1/2 of a second. Right, so that's 18 meters per second. Okay. So again, this is still an average velocity between 2.5 and 3 seconds. Right. And yet this still doesn't tell us what the instantaneous velocity is. But maybe you can see where we're going with this, right? I can use an even shorter interval. I can get closer to 3 seconds. Let's say I want the average velocity from 2.9 seconds to 3 seconds. Okay. So I still use s of 3 minus s of 2.9 divided by 3 minus 2.9. So s of 3 is still 9 meters. And now I have to calculate s of 2.9. And again, I'll just use my calculator. And I get 6.728. Again, in meters, right? And 3 minus 2.9 is just 0.1 seconds. So, again, using my calculator, 9 minus 6.728 is 2.272 divided by 0.1. So we end up with 22.72 meters per second. Okay, so that's still an average velocity, but it's an average velocity over this 1/10 of a second time interval, right? From 2.9 to 3 seconds. So, right? So that's pretty close to just 3 seconds, right? But it's still not quite exactly 3 seconds. It's 1/10 of a second before that. But over that interval, that's how fast we were traveling, 22.72 meters per second. So it might be pretty close to the instantaneous velocity, but we're not quite there yet. Right? If you want to get closer, you can see I'm running out of space here, but let's do one more. Let's do the average velocity from, let's do 2.9999 seconds to 3 seconds. So 2.9999 is awfully close to 3. Right? So calculating this average velocity, now I think we can say this will be very close to the instantaneous velocity. Right. Again, it probably won't be exact, but it'll be very close. All right, so s of 3 is still 9. And s of 2.9999 is about 8.9976. And there's a little bit of an error, but that's good enough. This will just be approximate. And the time difference is 0.0001 seconds. Yep. So that's 1/10,000th of a second. Again, a very short time. Right. In that time, it traveled a distance of 0.0024 meters in 1 10,000ths of a second. So this is equal to, well, 24 meters per second. Okay. And remember, this is only approximate. It's actually, I think it's a little bit less than that. Right. So it should have been something like 23.99 something meters per second, right? Because this was not exact, I rounded. Right. So let's use the rounded value here. 24 meters per second is, again, the average velocity, but you can see it's going to be pretty close to the instantaneous velocity. And in fact, because I rounded, it turns out to be exactly the instantaneous velocity, but you know, we're just kind of guessing that at this point. Right. So yeah, by using this first value here, getting closer and closer to the 3 seconds, our average velocities are going to be much closer to the instantaneous velocity. Right? And this is the idea for a limit, right? A limit is what happens when you're getting closer and closer to something, but without actually necessarily getting there. Now, in this case, we actually got there, right? But that was because of round-off error. Right? If I did this correctly, I would have gotten something like 23.999 meters per second. But you can see that's very close to the instantaneous velocity, which turns out to be 24 meters per second. Right. Right. So we can sort of approximate the instantaneous velocity by using shorter and shorter time intervals that are closer and closer to this, right, this 3 seconds, which is where we wanted to calculate the instantaneous velocity. Right. So at 3 seconds, we are at position 9 meters. We calculated that way up here. That's the 9 meters. But we also now know how fast we were traveling. We were traveling at approximately 24 meters per second. So that's the instantaneous velocity. If I look down at my speedometer at that moment, at 3 seconds, that's how fast we were going. So continuing with this example, we have the same position function, right? 2t cubed minus 5t squared, right? And so I want to calculate the average velocity again, but this time from t equals 3 seconds to t equals 4 seconds, right? And I reproduced the table I calculated earlier. So to calculate the average velocity, we're just going to plug in, right? So in this case, a is 3 and b is 4. So s of b is s of 4 minus s of a, it's s of 3, divided by 4 minus 3. So s of 4, remember, was 48 meters. S of 3 was 9 meters, divided by 4 minus 3, 4 seconds minus 3 seconds. So, right, so the distance we traveled is 39 meters, right, divided by 1 second. So 39 meters per second. Right. So, right. So the next example I want to do is just to show that our previous answer, remember the instantaneous velocity, right, at t equals 3 seconds was about 24 meters per second, if I remember right. Right. And we calculated that using a very short time interval right before 3 seconds, right? So 2.9999 to 3 seconds. Right. But I can also use, say, an interval from 3 seconds to something a little bit later, like maybe 3.1 seconds. Right? Or we can get even shorter, right? 3.01 seconds or 3.001 seconds. But let's do this one for now, right? So this is going to be s of 3.1 again, we're calculating the average velocity. So s of 3.1 minus s of 3 over 3.1 minus 3. Okay, so what's s of 3.1? It's 11.532. And then minus 9 over 3.1 minus 3. Okay, so 11.532 minus 9 is 2.532 divided by 0.1. So this will be 25.32 meters per second. Okay. And if you're wondering how did I get this 11.532, right, remember the function was 2t cubed minus 5t squared. So I just plugged that in my calculator, and I ended up with 11.532. Okay. Right. And we can see that's, well, it's probably closer to 25 meters per second than 24. But remember that 3.1 might not be close enough, right? We want to get closer to 3. So how about between 3 seconds and 3.01 seconds? What's the average velocity now? Well, so I just have to calculate s of 3.01. We already know s of 3, right, was 9. So s of 3.01, again, just using my calculator, it's going to be 9.241302. Right. And then minus 9 divided by 0.01. So we have 0.241302 divided by 0.01. So this is going to be 24.1302 meters per second. Again, that's an average velocity between 3 seconds and 3.01 seconds. So in that 1/100th of a second interval, that's the average velocity. And you can see we're getting awfully close to 24 meters per second. Right. So if we do one last example, I'll do 3.001. What's the average velocity now? Right. It's just s of 3.001 minus s of 3 divided by 3.001 minus 3. Right. And again, just to show you where this number comes from, to calculate s of 3.001, you just plug it into the same function, right? 2 times 3.001 cubed minus 5 times 3.001 squared. And that number turns out to be 9.024013002. That's probably just approximate, but good enough, right? And then the same minus 9 over, again, the time interval here is just 1/10,000, I'm sorry, 1/1000th of a second. Okay. So we get 0.02, oops, 0, all right. So the difference is 0.024013002 divided by 1/1000th. Right. So that turns out to be 24.013002 meters per second. Okay, so now you see the pattern here, right? You probably already saw the pattern, but now it's even more clear. Right? So the closer this second time here, right, this b, so in this case b was 3.001, the closer that gets to 3, the closer the average velocity gets to 24. And then that becomes the instantaneous velocity, which we already know turns out to be exactly 24 meters per second. Right. Right. In other words, the more zeros you add to the time, right? If I did 3.000001 second for my b, right? I'm just adding more zeros after the decimal point for the velocity. The average velocity will be something like 24.0013 and so on, right? And yeah, so that just gets closer to 24. So that's the idea of a limit. Right? A limit is what happens when you're getting closer and closer to something, right? To some number. Right? And so to make this a little more formal, right? So we have the average velocity. We know the formula for that, right? Given the position function s of t, right? The average velocity is s of b minus s of a divided by b minus a. So this is the average velocity over the interval, right, between t equals a and t equals b. Right. Use either notation. Okay. So then the instantaneous velocity right, at a given moment, right, at time, let's say t equals a, well, this is what happens, right, when we take the limit as b gets closer and closer to a. Right? So as b gets closer and closer to a, right, again, we can't plug in a for b. We've tried that already, right? And we got 0 over 0, which doesn't tell us anything, right? But if we pick a time, say t, right, which is close to b, right, which is very near b, near a, right? So as t approaches a, or gets close to a, right, then this quantity approaches the instantaneous velocity at time t equals a. Instantaneous. Okay. Right, and we can just call that the velocity v at time t equals a. Right. So this is what we're going to do a little bit later in the next chapter. But this is a nice preview of what, why we need to calculate limits, and that's something that will occupy for the rest of the chapter. How do we calculate a limit more precisely, right? So I hope this helps, at least gives you the idea for calculating average velocity. So most of the problems in the homework are calculating average velocities, and in some cases it's calculating several average velocities where the time, right, gets close to one particular number, right? In this case, it was 3, but it could be a different number in the homework. So I hope this helps.